So this was one of those lectures that just rounds a few different things together to make sense. This is all stuff that I think you really know and understand, and it'll just clarify some things in different ways. So hopefully this is all going to be pretty easy going through this. And then this is one of the last tough lectures, as it were, right? So after this, there's stress reactions next week, and you'll do your evaluations next week in class. And I'm still trying to work on getting someone from the coroner's office to come over, medical examiner's office to come over to do the autopsy presentation. That guy cannot. I'll only one way to get there. Then I have one that I can present that I'll show you all a bunch of different things that we've seen from autopsies in the past. That can help. But that's my intent moving forward is where we go with things. The night of your final is the night, or is the second day of state council, and it's in Saratoga instead of Troy, so it's gonna be a little bit longer for me to get back. I'm gonna work with Bernadette so that y'all can start your finals before I get here, and then I'll get here and break down, go over them. Okay? So that's kind of the plan moving forward in the next couple of weeks as to what we do. Any questions? All right. So let's go through this. Did anybody look through this presentation at all? Sort of skim, maybe read through.
Skimmed it.
Skimmed it. Okay. It's all inside. Yeah. No. All right. Okay. So let's talk about hypoperfusion. So we learned a lot about traumatic things from wars. We get a lot of data information. There's a lot of studies and research that happens, and so we really get a lot of things out of what happens when we tragically tear each other apart and try and figure out how we can get us back together. And so a lot of this stems from there. Some of the most recent things were tourniquets and a lot of the different technologies now in place with oxygen delivery kinds of systems and volume expanders comes from those events. So when we look at hypoperfusion, the big thing that should come to mind is that you're not getting good gas exchange at the cellular level. That's really what it comes down to. And so what factors go into you not getting good gas exchange at the cellular level? Well, there's a ton of things, right? And so we'll just go through a bunch of stuff here, see what kind of hits the wall, what questions you have, what really makes sense, and then work through what these are. There's a lot of sort of, I don't want to call it redundancy necessarily, but overcompensation in the system, right? So we only use 25% of the oxygen capillary level in the bodies at rest. That is really good, right? That means that you can have a whole lot of systems not working all that well and still be well perfused, right? And for some of us, that works out really well. So when you think of years of eating Twinkies and ring dings or fats or not exercising or any of those kinds of things, smoking, high cholesterol, like all that stuff, those are all little notches against the body's effectiveness at giving the cells oxygen. And while you may be doing okay at rest, as soon as you run up a flight of stairs, exert yourself, exercise, whatever, and you come short of breath, it really then is evident that you're not compensating the way you should be, and your body's not working as efficiently as it could be, right? So that 25% number is an important number to realize as well. Okay. So we've got all these types of metabolism going on to create energy, right? We talked about aerobic metabolism, getting 36 generally, could be 38, 34, somewhere in there, units of ATP. We talked about electron transport phosphorylation, glycolysis as part of this. And all those are good basic mechanisms of when the body's not stressed, creating good energy. When the body then gets stressed and cells don't get the oxygen they need because our oxygen demand goes up 2, sometimes 3-fold. If you can't deliver to the cells, then you have hypoperfusion. Even if you have blood going to there, if it's not containing oxygen and you're not offloading at the cellular level, that's bad at the rate the cells need. And so since it goes up so much, the cells then go into anaerobic metabolism, and then we only get 2 units of energy. We get a lot of garbage, waste products that are delivered out of this as well, including a lot of acids, carbon dioxide, etc. So getting into anaerobic metabolism is a bad thing, and we want to try and reduce that as much as possible. So that's got less energy, all this other stuff we just talked about. Now, the less energy, the acidosis, the high amounts of CO2, the lactic acids, all that stuff are not good things for the organs and the tissues that are in that environment, right? And so that's bad. What does that do? Further reduces the capabilities of those tissues and organs, which then further reduces perfusion, which then further reduces the abilities of those organs, and this ends up being this perpetuating cycle that's a spiral. So when we talk about oxygen delivery, we have all these different mechanisms in relation to the cardiovascular system, right? If we talk about, and we did this already, about oxygen getting in, going through all the normal mechanisms of the respiratory system, down into the alveoli, gas exchange occurring at the alveolar level, and then finally now it's getting into the circulatory system and going out to the rest of the body. We have these things that we talked about. Out of all of this, you should understand it generally, but know that the last 2 things are really important. Cardiac output is stroke volume times heart rate. Okay, those things you know. So what's stroke volume? Per stroke per heartbeat, right? And so folks that are mechanically inclined will talk about 2-stroke engines, 4-stroke engines, that kind of thing, right? And it's compression based on movement of the cylinder and mixing of gas and air. Same kind of idea. Each heartbeat puts out a particular amount of cardiac output, and stroke volume is a piece of that. Heart rate is the other piece of that. And so if your heart is putting out a certain amount of stroke volume, but your rate is 50, is that going to give you perfusion that you need? Maybe if you're sitting on the couch watching late night comedy, eat potato chips, right? Doing whatever. Or grading abstracts with the second glass of wine, right? Maybe that's the way it works for you. But as soon as you increase the demand, that heart rate may not be good enough, so I don't have the cardiac output I need. And so you have to increase the heart rate to get the cardiac output. Make sense? Yes? Okay. Why do children have higher heart rates than adults?
Their stroke volume's lower.
Because their stroke volume is lower. That's exactly right. So their heart is so tiny comparatively that they don't have cardiac output the way that we have cardiac output, because we can put more volume in each stroke, each heartbeat, than they can. So their rate has to be faster to get cardiac output to match perfusion needs. All right. So stroke volume, consequence of 3 things: preload, afterload, contractility. So what is preload? What does pre mean? Before, and load would be an amount, right? And so preload is the amount of blood available to the left ventricle prior to contraction. It's also called left ventricular end diastolic pressure. And so if you have a low preload, a low amount of blood available to the ventricle before it contracts, are you going to have a good stroke volume? No. And so what are things that can cause low preload? Hypovolemia. So if you don't have blood in the system, it ain't getting to the heart. Okay. What else? Congestive heart failure. Right-sided heart failure. Right. Yep. And so if the right side of the heart is not pumping to the left side, then you don't have preload to the left side of the heart. You don't have good stroke volume. You don't have good cardiac output. Right. What else? AFib or any other kinds of electrical disturbances that would reduce the amount of preload going to the left side. What else? Tachycardia, MIs.
The valve is not.
The valve, like valve regurgitation, right? Okay, tricuspid regurgitation, or even bicuspid regurgitation. What else? Compression of the heart, right? So the person has a pneumothorax, and it squeezes against the superior and inferior vena cava. You have reduced blood flow going to the right side, which means you've got reduced blood flow going out to the left side, which means you have low stroke volume, which means you have low cardiac output. Okay? And that could be a pneumothorax, hemothorax, hemopneumothorax, any of those kinds of things that cause it. It could also be pericarditis, compressing the heart, right? Where the pericardium is inflamed, fluid ends up in that space and compresses the heart, and then you don't get good cardiac output because you good filling on either the right or the left side. So these are all ideas of preload and what happens there, right? So if you don't have good preload, you don't have good stroke volume. If you don't have good stroke volume, regardless of how fast the heart goes, up to a point, you don't have good cardiac output. Make sense? All right. What's afterload? That's exactly right. And so that's blood pressure, and we're talking about more diastolic blood pressure, right? The resting potential of the circulatory system. The heart has to overcome diastolic pressure to move or get any kind of flow forward in some way, shape, or form. So think of it this way: if you're trying to get into the classroom and someone's holding the door closed, right? You have to overcome the force of that person trying to hold the door closed to get everybody else to come in. If you have a high diastolic pressure or a high resting pressure, the heart has to work harder to overcome it to get blood flow in the system. Yeah? If the heart can't do that because it's going too fast already, or because of congestive heart failure, or because of arrhythmias, or because of some kind of a compression in some way, shape, or form, then it can't do it, it won't do it, and what happens to cardiac output? It drops, right? And so what causes high diastolic pressures? Say again? Yeah, so atherosclerosis.
Hypertension.
Pulmonary hypertension could do it to the right heart, right, where the right heart can't then move things through the respiratory tree, vascular tree into the left side. Hypertension. Say again? Stroke. It's more the hypertension. The stroke would be a consequence of the hypertension. Okay? And so, yeah, so these are all reasons that you don't get good cardiac output because you've got too high of an afterload. So when you've got a patient with a blood pressure of 130/70, is that terribly bad? Well, it's not great. 70 is a good number. I like that number because that's at rest, right? And the 130, all right, so for some reason they have a higher systolic, the heart's really pumping hard, don't know why. Maybe they're excited, maybe they're, a lot of things going on, they're anxious, whatever happens to be, some kind of reason to cause that. 130/100. That's not great because now you've gone up 30 points in the resting state, that afterload, that resting perspective of the vascular system. That's not good. It doesn't handle that for long. Think of that Think of that pressure in the capillary bed, right? That's why people with hypertension usually end up with bloody noses, because that high pressure breaks the capillary bed in areas where it's readily accessible to the outside, and so you get a bloody nose out of that. Sometimes people with hypertension will start off with sniffles as well, because you end up getting that high hydrostatic pressure in the capillary bed, and you get fluid leaking out into those capillaries in the nose, and that can end up being some sign of it. So the body has to have good preload, overcome afterload, have good stroke volume to get decent cardiac output. And that cardiac output is a number that kind of fluctuates a little bit based on what the needs are of the system. Does that all make sense? Yeah? All right, cool. All right. Cardiac output itself only works to a point, right? And so you said the heart goes faster, and it does. And so you see this in people who start, that are hypertensive. They'll become tachycardic, and they're trying to maintain that cardiac output by increasing the rate. And so that works up to about 150 beats per minute. And then we get this thing called Starling's curve, right? Where it's only effective up to a point, and then finally the heart's beating so fast that it doesn't have time to fill. And if it doesn't have time to fill, it doesn't have what? It doesn't have volume. It doesn't have the right preload. You can't get blood in fast enough to fill the ventricle to have cardiac output, because it's just tacking away too fast. Okay, it's just not going to work. And so that's Starling's curve. So up to a certain amount, yeah, tachycardia is going to work. But once you reach that threshold, then the faster the heart goes, you actually get diminishing returns, as evidenced by the back end of this curve over here. All right. We talked about preload and left ventricular diastolic volume. Talked about afterload. We talked about contractility a bit. And we've seen the wheels on the bus go round and round. So oxygen intake, we've got arterial saturation. This is just an example of the capillaries, capillary bed, and what's offloaded. If we have arterial sat 95 to 100, venous sat of 70 to 75, that means we use 25% in the capillary bed at rest. And when we say what happens to this under stress, duress, exercise, or other things, it could double or triple, right? Okay. Okay, good. When we get to this point where oxygen is, the demand overcomes the supply, we now have hypoperfusion. Right? And there's a lot of factors that could diminish supply. There are a number of factors that can increase demand. And so those are things that you need to look at in your patient. Do they have supply? How do we improve it? What are some of the things we do? Supplemental oxygen, CPAP. CPAP. Okay, what else? Sometimes intubation if we need to maintain airway control and positive pressure ventilation. What else?
Also BVM.
AVM ventilations. Keep going. Intubation. Meds like what? Albuterol, right? Okay. Things to open up the airways. All right, that's good to get more oxygen in. What did you say? Nobody excess. Acids or acid, yeah. Possibly. That talks a little bit in a different system, but okay. So you're talking about all these airway maneuvers, right?
Right.
Say again?
Cardiac medications,
Cardiac.
if it's from cardiac origin.
Cardiac medications. Okay, yeah. So things to speed up the heart or slow it down if it's going too fast. things that increase cardiac output by really whipping the heart, right? Like norepinephrine drips. What else? Giving fluid, right? We can give fluid to help in cases where someone's septic or where they're really hypotensive because of a volume issue. So we can look at a person and try and fix the fact that they're not getting oxygen and or their perfusion is bad because of the heart, the vessels, or the fluid in the system, right? Does that all make sense? Okay. Remember the question about third spacing, right? Where's the water? Is it available? How does it help? How does it not help? This plays a role in that as well, especially the capillary bed, as to whether fluid is moving into or out of the vascular system in that particular state. Okay? All right. So when we talk about hypoperfusion, there's three typical areas where there could be a problem. So the heart, we talked about all those things. What other things could be wrong with the heart? We talked about a lot of issues earlier. Anything else that we need to add to that? Cardiac disease, genital issues, rhythm disturbances, whether it's being squished or not, left ventricular hypertrophy. Say again? Electrolyte imbalances, sure, absolutely. Hyperkalemia, hypokalemia, calcemia, those kinds of things.
Heart attacks.
For sure, right? If there's structural damage to the heart in some way, shape, or form. Right, so these are all reasons why the heart may just not work, including damage, like there's a hole in it because someone stabbed it, blunt trauma, any of those kinds of things. Those are issues with the pump, right? What kinds of issues impact the container? Sepsis absolutely does. Yes. Amputations. So amputations are interesting. Initially, the blood vessels will constrict and kind of suck in a little bit and stop the bleeding. But then if it's not treated appropriately, then you can bleed out through there, especially if it ends up being like a really jagged, unclean cut, right? So loss of integrity of the container,
Plaque buildup.
for sure. Atherosclerosis, right? We talked about that. Crushing syndrome, compartment syndrome. Okay, all of these things are ways to affect the container in some way, shape, or form. We'll talk about a few more as we go through. And then problems with the blood, right? So if we don't have enough fluid, if we've got third spaced fluid, if there's problems with the hemoglobin's ability to have affinity for oxygen or not, whether the hemoglobin is deranged or not, whether it can carry oxygen or not, all those kinds of things. Whether there's enough of it or not. So all of these things are issues with the fluid itself that's in the container. And then you can combine all of those, right? So you don't have to have just one of those things. You can have a number of those things going on at the same time. So that's bad. So the guy that has an MI while he's driving down the road crashes his car, and now you've got not only cardiac issues from the MI, but potentially traumatic issues as well that are going on. Okay? All right. So here's an issue with the container. So you can clearly see in one slide on the left, we've got a nice good open branch, but on the right we don't because it's occluded. And so that's just a good example of container issue. So you talked about anaphylaxis, right? Allergic reactions. And so here are some other reasons for classifications of shock when we talk about those shock states and reasons for being in that hypoperfusive shock state. So we've got hypovolemia, which we talked about, cardiogenic shock, we talked about and the reasons for that, neurogenic shock, and so we didn't talk a lot about this. Neurogenic and septic shock have very, very similar end results, but the reasons for them, one is a neurogenic issue, the other is a chemical issue. So in vasogenic reactions, such as anaphylaxis, it's it's a dilation because of a chemical issue, not because of a neurological one. So we had a guy years ago that crashed his motorcycle on Seven Lakes Drive down in North Rockland, and we got on the scene. He was just laying there talking to us, red as can be, and his vasculature looked like garden hoses. And he was as hypotensive as possible, right? And so he had ended up in neurogenic shock because of spinal cord injury, lost the ability to constrict his vessels, became hypotensive because the size of the container increased beyond the fluid in it, and his skin was all red because the container was huge, right? And so, so that just blood being red, like you could, like his skin was red. Not that he was bleeding out into his skin, but because his vasculature was so big. And back then, eons ago, backboard, mask, pants, 2 liters of fluid, and we got down to Medic Hospital, and the doc went berserk. We're like, dude's a neurogenic shock. Like, what do you want us to do? Kind of thing, right? And so that's an example of someone being in neurogenic shock, where you lose the ability to control the size of the vasculature. It opens up, drops the pressure, you lose all the fluid, and you're not losing it, but you don't have enough fluid in the system for the space that the system's in, right? Kind of like if we had all of us in here, it's great, it's nice. But then if we put all of us inside Giant Stadium and tried to do this, but spaced everybody out, ineffective as all that, right? Okay, so that's how neurogenic and vasogenic shocks operate. They're just different mechanisms that start the process. One is neurological, the other one is chemical. All right, so in hypovolemic, we've got all these things going on. We've got problems with volume, which leads to preload issues. And when we talk about classes of hypovolemic shock, we've got these 4 classes here. First one, 15%, 750 mLs. Person will become a little tachycardic, totally fine. They'll compensate a bit, totally fine. And if it's not resolved, it moves into the next one. 750 mLs, how much is that actual volume? I know it's 750 mLs, but what's practical? What do you got? It's exactly a bottle of wine, 750 mLs. Perfect, right there, right? Okay, yeah, 750 mLs, 1 bottle of wine. If you pour a bottle of wine out on the floor, please don't do that. Many times we're crying, right? That's a class 1 volume loss in the system. It's a little bit less than 15%. Okay. When we give fluids to someone, how much are we supposed to give? We start off with like a 250 ml bolus, maybe go up to 500 mLs, right? And then more if we need to. It really depends on the situation. In a hypovolemic situation, because of loss of integrity of the container, meaning that the vasculature has broken open and the person's bleeding out on the ground, you give a lot of fluid, what are you doing?
Kool-Aid.
Straight Kool-Aid, right? And you're putting more of the hemoglobin out on the ground, and now you're losing oxygen carrying capacity. So unless you stop the bleeding, you're not doing anything for the person. When you have someone in anaphylaxis, or in septic shock, or in neurogenic shock, when you give them 500 mLs, what are you doing? You're trying to fill the container enough. You still have the same amount of hemoglobin, but remember now that it's diluted because the size of the container is bigger, and so you're not going to have the same effects as you would if the container size was smaller. So we try and change the size of the container, stop the process, fill it up a little bit so that your hematocrit doesn't change so much. All right, so 1 bottle of wine gives you a class 1 hypovolemic reaction. 2 bottles of wine, 15 to 30%. Now the person has orthostatic changes, cool, clammy skin because they're not perfusing very well, and the body's going to start shunting from areas that doesn't necessarily need to have blood to it, areas that absolutely need blood to them. Class 3, they now become pretty hypotensive, and we see neurological changes, right? Anxious, combative, because the brain needs two things for sure. It needs glucose and it needs oxygen. And if it doesn't get one or the other, it gets loopy. And so in this case, they're not getting either. So you'll start seeing neurological changes as well in the individual, right? And then finally you get, somewhere around 2,000 mLs and they're ready to cope, which is a huge amount of blood loss. So that's good ways of remembering these different stages of hypovolemia. I do not expect you to be on scene and tell your paramedic partner, oh, looks like we have a stage 2 hypovolemic issue here, right? No, like you're going to understand though what's going on with the person and start treating them accordingly, right? And those are the things you need to look
I don't think I'm ever gonna be able to look at another like scene where someone's bleeding, like, how many bottles of wine is that?
at. You're really like, Violante's guys.
I just did the math. 2,000 mL is like 2.5 bottles, in case anyone's wondering.
Yeah. Okay, so we do have these compensatory mechanisms, right? It's not like a total free for all. The body's not going to be like, oh, well, things suck, it's bad news for us here. So we've got these baroreceptors in the atrium, aorta, carotid. Why are they in these different places? Well, so they're in the atrium to make sure that you have enough blood coming to the heart, right? So if the baroreceptor says pressure's low getting to the heart, what's the body's response going to be? Get more blood to the heart, right? If there's too much blood coming to the heart, the pressure's too high, it's going to say, whoa, slow things down. Heart rate's got to come down, maybe reduce contractility, those kinds of things, yeah? Same thing for the aorta going out to the rest of the body, and same thing for the carotid arteries, right? So if you have, you don't want to blow the brain out the top of your head just because the system's gone haywire. And so that's another mechanism to ensure that you're not so hypertensive that you're creating a stroke situation because the person's hypertensive. Sometimes it happens, and there's a number of mechanisms involved in that, but that's one of the reasons why the body didn't put these there on purpose. People evolved to have these things in these places for these reasons. And we're gaining more and more understanding of all this as time goes on. All right, so that's one thing, is to look at where the pressure is in these areas and increase it or decrease it accordingly. Ways to do that: epinephrine, norepinephrine release, peripheral vascular resistance, shunting. All these are methods of improving perfusion. Oh my God, here we are again.
Rosa, you're up.
So this happens, right? We talked about this before. All right, so you all know this. I don't have to go over this, but the body is working to try and retain fluids, increase pressure, and this is a mechanism, a feedback mechanism to ensure that some of the stuff happens, but then doesn't go overboard. Okay? So let's take a look at a renal artery stenosis. What do you think is going to happen here? What happens to the perfusion in the kidney? It's reduced. What's the kidney going to do?
Increase blood pressure?
It's going to produce renin because the concern is that the pressure is too low getting to the kidney, and so therefore you have to increase pressure in the system to increase perfusion for the kidney. What does that do to the rest of the pressure in the system? It increases it. Is that good or bad for the kidney? Probably better for the kidney, but it's not good for the rest of the system. Thank God we have two kidneys, right? And so there's some regulation of this a little bit. But that is what's possible in renal artery stenosis. So we've talked about all these other compensations. And so this is what happens now in the vascular bed, right? So we've got this oncotic pool of fluid initially. So we've got a a little bit of hypoperfusion going on. There's stagnation in the capillary bed. And so because of some of that stagnation, we get fluid shifted into the vascular space because there's more proteins and such. It's a hypertonic area inside the vasculature as compared to the area outside the vasculature. But then these vessels will leak some of those proteins out into the area because of that stagnation, secondarily now. And then what happens? The fluid follows them, right? Because there's a little bit of an oncotic pull. It's now hypertonic outside of the vasculature, and more fluid goes outside the vasculature, which further reduces the pressure in the capillary bed, but it increases interstitial pressure in that area, right? You're with me? Okay? And so fluid shifts back out to the vascular space, out. This is one side of it, right? And movement of proteins and some electrolytes and such. Additionally, now we talk about hydrostatic pressure. So initially, both sphincters, pre and post capillary, will close with no movement in or out. What does that do in the capillary bed? Oxygen gets moved out of the vascular space into the cells, gets used up, and then we've got carbon dioxide being produced. That proliferates the interstitial space and the vascular space. Toxins get produced, CO2, acids, all those things start proliferating both spaces, yes? Okay? So we get all that stuff in both of those areas. Then the precapillary sphincter opens, and you have movement of fluid in. But if you don't have movement of fluid out, we have a high hydrostatic pressure in the vascular space, and what happens to the fluid? It gets pushed out into the capillary bed, and so now you've got, again, increased interstitial pressure in that capillary bed. Right, and so that's this third area over there. Eventually, then you'll get the post-capillary sphincters opening up, and you get a movement of all of this junk out from the capillary bed into the system. And so think of a case, this is a good example of it, of kind of what happens, but this is a mechanical example of what's happening in the capillary bed, right? So you get a person in a car accident with a dash on them, on their lap, right? And so you have reduced blood flow down to the lower extremities for a significant amount of time until they roll the dash or move the dash off of those lower extremities, right? Well, what's been happening in those lower extremities? Buildup of toxins, carbon dioxide, acids, anaerobic metabolism, all kinds of stuff happening, right? And when we immediately move all that stuff back into the system, the person immediately goes into a flash metabolic acidosis. And we have all those toxins in there, which is why before we roll the dash on a person, we say, hang on, let me start getting some fluids, let me hyperoxygenate, let me give them bicarb, let me give them calcium, and let me give them some electrolytes to combat this rapid metabolic acidosis that's about to happen. In addition, we have a tremendous fluid loss that can occur, which is why we're also giving them a little bit of a fluid challenge up front. Make sense?
Mm-hmm.
Okay? So some of that's happening there. All right. Other compensations that occur, we've got decreased coronary perfusion, which leads to myocardial ischemia. If the heart's not working well, it's not going to push the blood out to the system, which means the heart's going to be the first recipient when the valves close to not get as much blood coming back to it. Acidosis will lead to vasodilation. Not all great. And if that's not changed, then the shock state just keeps going. So this is this irreversible move down into circling the drain into the toilet, right? So what do we have to do? Fix oxygenation, fix perfusion, stop the bleeding, change the size of the container, stop whatever is causing the size of the container to change. We may or may not be able to do that. We can't really do that in neurological states, right? But we can do it in anaphylactic, septic, or other conditions. We can fill the container up, stop the anaphylactic process in some way, shape, or form, and help to change it and reduce it. So when we actually talk about hypovolemia, there's these three different sort of areas here: compensated, decompensated, reversible. Right. So in compensated, we see that the heart rate goes up, but the blood pressure also goes up. Now, why, if we have a loss of pressure and hypoperfusion, would we have an initial increase in blood pressure? The heart's pumping hard initially, right? And so as the body, right before it gets into a compensated or decompensated state, it'll compensate, and it's right on the edge, and it has the fluid in there to be able to create the pressure if the heart goes a little bit faster. You have initial higher blood pressures in this. If you keep losing blood or the container continues to increase in size without filling itself, then you get into decompensated situation. In this case, it's marked by the heart rate still going up, not necessarily to that 150 rate, but it's gonna go up quite a bit, and you're gonna have a drop in blood pressure because the heart won't be able to maintain it. So you've now gone into a decompensated state. When it comes to reversible, that's where heart can't keep up, it's not getting oxygen, so it's not going to work. There's no preload, you've got reduced cardiac output, even though you have really no afterload to go against, it's just an open container you're trying to and so that's down to irreversible. Okay, we talked about cardiogenic and these different factors. We talked about shock here. MIs, you can have loss of 40% cardiac output. All right, so this is my sort of quick interpretation on looking at 12 lead EKGs. And I use the cursor because you can't really see the pointer on this thing. All right, so here's our 12 lead EKG, right? So we've got leads 1, 2, 3, RL and F, and then V1, 2, 3, 4, 5, and 6. So typically say that lead 2, 3, and AVF are inferior wall, right-sided heart failure leads, right? So if you look at this heart, and the heart typically is on its side, so this is the inferior side. These leads correlate to this area of the heart right here, right-sided heart failure. So if you see changes in T waves in 2, 3, and AVF, that's indicative of problems with the right side of the heart. And we'll talk about what those will look like in a second here. If we look at V1 and V2, where are those more closely associated to the heart? Into the septal area, right? Okay. 3 and 4 are sort of more an anterior part of the heart, and then 5 and 6 are lateral parts of the heart, of the left ventricle. So these are all really septum, anterior, left side of the heart. And then you can even see lead 1 as a complementary change with V6. If you see something in 5, 6, and 1, that's indicative of left-sided going around to the back of the heart. So when you look at your 12 lead, it's actually pretty simple to figure out what's going on with the heart. Changes in 2, 3 AVF, right-sided, V1 and V2, anterior, or septal, 3 and 4, anterior, 5 and 6 lateral, or left-sided. Okay, make sense? Okay.
V3 and V4 were
Anterior. All right, so let's take a look at right-sided heart failure here. So you can see 2, 3, and AVF, right? You can see this ST elevation here, very pronounced on this EKG. Squint your eyes so you can see it. And so what's happening? There's a problem with the right side. And so on the right side, if the right side is not pumping blood into the lungs and then through to the left side of the heart, where is that blood going? Nowhere. It's not moving forward, right? I mean, a small amount might be moving forward, but it gets backed up into the system. And so where does it back up? Into the superior inferior vena cava, and then into the splanchnic system, because it's all backed up. But what happens to the lungs? Is there fluid backing up in the lungs? No, there's not. Okay? And so the lungs are not going to be wet, right? They're going to be dry. Normal clear sounding lungs. Right side of heart failure. Does that make sense? We have good cardiac output? Not so much. Why? Because we don't have preload. The left ventricle. Okay? All right, so let's take a look at the left side. So we can see V1, 2, 3, 4, 5, and 6 up there. It's really starting to be pronounced in V1, 2, and 3. For sure, we can see something not so much in 4, 5, and 6. So this is what kind of a MI?
All going into
Septo-anterior, right? A little bit in V1, 2, 3, maybe a smidge in 4, but not really, right? So septal to anterior. So if you have a septal wall MI, it's very possible you're going to get electrical changes and all kinds of funky rhythms happening because the septum is really affected. And so what comes down through the septum? Yeah, the bundle hits like the entire movement of the electrical system of the heart. So if that's affected, you can start seeing some funky things happening. All right, so in this case, if the left side is not really working all that well, then are you going to have good cardiac output? Not so much. In this case, where does the blood back go? Into the pulmonary tree, right? And so in that case, are your lungs going to be wet? Yeah, very possibly. So low cardiac output, wet lungs, some EKG changes there, and then that's a problem. That's right-sided heart failure. So all these are indications of right-sided heart failure. Left-sided heart failure. Does left-sided heart failure, can that cause right-sided heart failure? Sure can. Absolutely it can, right? Because the right side will not be able to work, and so then you'll have a backup right side as well into the body. It's pronounced and prolonged. All right, so what do we do for these folks, right? So we've got this person over here that's got inferior wall MI, and we've got poor cardiac output, but we can see it's an MI that's going on. They may have a decent pressure. They may have at least a little bit of a pressure for some things that are moving through. What do we do? Where is blood not getting? To the lungs and then the left ventricle, right? So blood is not getting to the left ventricle. What do we do to get blood to the left ventricle? Increased preload. How do we do that? Fluids, absolutely. Right-sided heart failure, give that person some fluids. Okay, we want to move the blood into the left side as much as possible. It's not going to be very efficient, but that's something that we can do. Can we give nitrates to the person? Not if it's inferior, right? This person needs fluids to get blood out to the left side so you can perfuse the rest of the body. Is it good for the heart? No, not great for the heart. None of these things are good for the heart. Nitrates are helpful to some extent as long as you've got a decent pressure to help increase the size of the vasculature to the heart so that it gets more oxygen. Okay, so that's fine. That's okay to do if you have a decent pressure to do, but they need fluids. Right-sided heart failure. Left-sided heart failure. What do we do for this person? Do they need fluids? No, they don't need fluids. Okay, do they need nitrates? Sure, but what happens when you give nitrates? What's the effect of nitrates? Decreases the blood pressure because it opens up the vasculature, right? And so is that good for the system where you're looking for cardiac output and you don't have so much? Not so much. So what are the things that we do for left-sided heart failure? If we don't have a decent pressure, we can't give nitrates. Obviously, we're not going to give fluids. What do we do in that case?
Drive quickly.
Yes. And
or CPAP.
yeah, you can do some of that stuff. So some of the problem with CPAP is that it potentially increases pulmonary pressures and thoracic pressures, which ends up being problematic because then that increases afterload, and that's not good for the system, right? You could do that though if you need to, but in this case, you're going to give things that are going to whip the heart, and that stuff isn't terribly good for the heart, but at this point, I'll take the body over the heart in those situations, right? And so this will all come down the line. This will all make more sense when you get into cardiology or what you need to do right now. But I want you to understand a basic premise of how these things work. Does this all make sense? Yeah? Does any of this not make sense? Am I going too fast or too slow? You're all really quiet, so it's hard to gauge. Okay. All right, so this is a way to look at what side of the heart is working or not working. This is a cardiogenic issue. It's one of the reasons for poor perfusion, hypotension, and it's one of those things that you have to understand. Neurogenic, we talked about a bit. Spinal cord injuries, loss of sympathetic control, vasculature opens up. You don't have fluid to maintain the container, so you have to give some fluids to get into the container. Okay, vasogenic, so anaphylaxis, sepsis, MODS, which is multiple organ dysfunction syndrome. When you get one organ system that starts to fail, it impacts another organ system. If that organ system starts to fail and you get two or more organ systems that fail, you get into multiple organ dysfunction syndrome, and that's death. So all of these things are vasogenic reasons, same kind of neural involvement, but they're for chemical reasons. They're not for neurological reasons. Same kinds of things will happen. Okay? Especially in septic shock and some of these chemical reactions that occur are the reasons for the chemical expansion of the system. You get a lot of leakage from the vasculature. So not only does it open up in size, but then it opens up letting a lot of the proteins and such out, which then moves fluid out of the vascular space into the interstitial space as well. That's fluid is now called what? Not yet. It's third spaced, right? The fluid's now in a third space where it's lost into the interstitial space and isn't used. And we have to mitigate that to get it back into play, right? We don't want it hanging out in the interstitial space. And so those are things that happen in septic shock. So you've got low systemic vascular resistance, increased CO, warm extremities, eventually pooling, leakage, poor perfusion. That's movement of fluid out of the vascular space. The splanchnic bed has constricted as well. What is that? What's the splanchnic bed? Remember the splanchnic system right down in the mesentery, and you get movement of that blood resolve from those areas back into central circulation. And so that's helpful for a little while, but then you get, it's just sort of continues to spiral armor down, right? If you don't resolve the issue of putting some fluid back in, stopping the infection, the chemical mediator that's causing this to start with, then it's just going to continue. Okay? And that's why, especially in septic shock, we say the sooner you figure this out in the field and start fluids and let the hospital know, the better it is for the patient. So much better. You can start moving fluids into this person right away, and then we can start getting antibiotics on board. We can start doing some good fluid therapy and such in the hospital and get this reversed a bit. Okay. Good. So, assessment-wise, what are the things you're doing to look at all this stuff, right? So you're looking at the scene, get information there. ABCs of the patient, vital signs, all that jazz, get stuff there. History of the patient, medications they're on. All of these things are clues for you to know what's happening and why. You can understand what's happening to this person physiologically and look at their history and things that cause pathophysiological problems, then you can hopefully use the tools you have to fix the situation, or recognize you don't have the tools to fix the situation. We got to get you to a place that does have the tools to fix the situation. Okay? So these are all the things that you need to look at. Remember we talked earlier, a lot of you wrote this on your last quiz. So reasons for fluid volume deficit, and you talked about things like hypotension or CHF or this or that, right? Those are the results of fluid volume deficit, or the reasons of fluid volume deficit. And so when we look at things, we're looking at vital signs. We're looking at the results of poor perfusion, the results of hypotension, the results of no oxygen being at the tissues. Well, what caused that? That's the thing you have to fix too. Does that make sense?
Mhm.
Okay. All right. So we have all the stuff that we do. We talked about all this stuff. At the end of the day, I will say this. I'll ask you. People tease me about it out on the street still. Or if you want to, what do you think the cell needs in this situation? Right. But truly, what does the cell need? Is it getting what it needs? And how can you make sure it does get what it needs if it's not? Okay? So don't just focus on your findings, focus on what's creating those findings, and why the findings are what they are, to fix what the findings are telling you, which ultimately comes from what's happening at the cellular level. Does that make sense? Like, all right. Questions on this? All right, cool. So, what's next?
How about fridge? Kidding.
So, what's next week? Paper due next week?
Sorry to remind
Has this process been helpful of the different components moving up to get into the paper down? All right, good. Okay. I think a couple of you have already sent in papers to say, hey, can you give me a little feedback on this? That's great. I'll do that. I won't do it like Tuesday night, right? But I'll try and for sure make some time to. Okay, what else? Quiz, so you're going to study. You have an upcoming final to study for.
Have you made a determination as to whether or not the final sign?
No. We'll work on that. Okay, anything else? What?
Take time for us.
Take time for yourselves. Absolutely. All right.